The last section before break is about finding the area in a polar curve, and so we're going to calculate the area bounded by the polar curve or a part of the polar curve. Before we start, I want to emphasize a big difference when we talk about area with polar curves versus area with rectangular curves. When we find the area under a rectangular curve, we're just finding the area between the x-axis and the curve, so we're finding this area. And we approximate that area by drawing rectangles and adding up infinitely many rectangles. In a polar system, when we're finding the area, what we're actually going to be finding is a different area. We're going to be finding the area swept out on a certain interval. So it'll be this area here would be what we're finding when we're finding area. And the way we're going to do it is by adding up infinitely many slices that are more like slices of pie. So pieces of pizza or pie, we're adding up the area of infinitely many sectors. So that's the difference with polar. The area of a sector, the way you can figure it out, because the whole circle would be pi r squared, the area of a sector swept out by an angle would be a fraction of 2 pi. So it'd be whatever theta is over 2 pi times pi r squared. And so because the 2 pi would be the radians all the way around the circle, and so what happens is that this pi and this pi cancel out, so it's just going to be theta over 2 times the radius squared. But it comes from the area of a circle, and it's the fraction of the area of a circle you have. So here's the formula for area in polar coordinates. You're going to take 1/2 times your r function, your theta, your r function in terms of theta, and you square that function because that's how you do area of a sector. And then you add up infinitely many of them over a tiny change in theta. So our first question is find the area of the region enclosed by this curve, which is 2 plus 2 cosine theta. And I just want to emphasize that we want to think about kind of how we're stepping through this. So we want to think about, well, what happens when theta is 0? Well, when theta is 0, we have 2 plus 2 times 1. So we'd be starting our journey around this curve at this point, and then we're going to sweep out an area until we get to this point, which it would happen when 2 cosine of theta is equal to -2. So when cosine of theta is equal to -1, so at theta equals pi. So when we get halfway around the circle, we'd be here at pi. And then if we want to go all the way around, we would have to go all the way to 2 pi. So one way to do this would be to take double the area from 0 to pi, because that is exactly half of that region. And we would do 1/2 times r squared. And this would definitely be a calculator question. We wouldn't be trying to do that integral by hand. And another way to do it, if we wanted to do it all the way around the circle, we could take, sorry, not double. If we're going to go all the way around the circle instead of going halfway around the circle, we could sweep out from -pi to pi in order to get all the way around. So we could go from -pi to pi. So that's how we can find the area enclosed by that graph. Another example, we want to find the area of just one petal of this rose. So if I want to make one petal of the rose, well, if theta is equal to 0, I would start here. That would only be half of a petal. That would be like the next time when we get to the origin from there, so we sweep out this much, that would be when cosine of 2 theta is equal to 0, or when 2 theta is equal to pi over 2. So when theta is equal to pi over 4. And so If we sweep out from 0 to pi over 4, we would get half of a petal. So we could do 2 times the integral from 0 to pi over 4 of 1/2 times cosine of 2 theta squared. That would give us 1 petal. Or if we want to get the whole petal, we could do from negative pi over 4 to pi over 4. And then we wouldn't have to double it. Or we could go from pi over 2 until the next time we're at 0, which would be at, we'd go from pi over 4 until the next time we're at 0, which would be when 2 theta is equal to 3 pi over 2. So we could sweep out from pi over 4 to 3 pi over 4. And all of these would give us the area of just one petal of the rose. All right, so those are, that's how we use polar to find area. I forgot to mention that the way we would evaluate these integrals is just on our calculator. We wouldn't be expecting you to do these integrals by hand. You'd be just grabbing your calculator to find that area. Let's go ahead and do that for one of these petals. So if I'm on a calculator screen, and I prefer typing x's to typing thetas, but you could certainly use the letter theta if you like. That variable, remember, is a dummy variable. You would get the same answer either way. All right, so that's how you would do it. You would do it with your calculator to evaluate that area. All right, thank you so much. Bye.